Hey, good afternoon. I think it's afternoon. It's good afternoon, everybody. I'm going to quickly run through some slides to outline what we're doing within the Prospect Science team specifically. Some of the activities that we've been carrying out this last year with a focus actually on operations planning, although we are still quite away from operations. There will be a separate presentation tomorrow about the Prospect payload itself. So I'm not going to talk too much about that. However, I'll start just by giving you an overview of what Prospect is, for those of you who don't know. It's a complex payload, which comprises two main elements. The first is a drill called Proceed, which will be capable of acquiring samples at a maximum depth of 1 meter, hopefully icy frozen regolith samples, depending on whether or not we land in the correct place. And those samples will be acquired and then delivered to a laboratory called Prosper, which will be able to seal those samples in ovens, heat them, and then we will be able to analyze the resulting gases in two spectrometers. So we have a complex gas processing system and two spectrometers, which will allow us to look at the chemistry of everything which is released, and also help us to try to identify, if we find some volatiles, the origin of those volatiles as well. So as I say, there'll be a separate presentation on the payloads, the detail tomorrow, so I won't go into too much detail there. The goals of Prospect were established by the Prospect Science team. You can see them there on the left-hand side. We were originally, I think many of you know, we were originally being developed for a flight on cooperation with Roscosmos on Lunar 27. Events transpired that we all know about, which means we're not doing that anymore. And we have had to reorientate the project towards flight as part of one of NASA's funded CLIPS programs. So we are now manifested on CP22, which is expected to launch in the 27-28 timeframe. We've spent quite a lot of effort in evaluating the scientific impact of this transition to CLIPS, and we have discovered that we can actually still meet all of our science objectives, but in order for that to happen, things need to go really well. We need to plan very, very carefully, and this is especially the case from an operations perspective. The implications of from the operational side are quite severe. So here are some of those operational implications. Of course, when we're flying with a commercially provided lander, we need to accept that there's going to be a considerable increase in risk as well. And one of those biggest risks is with the operations. We have a much shorter mission lifetime than we had on Lunar 27. For Lunar 27, we were expecting to be operating for 1 year, 1 Earth year, that is. Now we have maximum 1 lunar day. So we've got to try and squeeze in 12 months worth of operations into 1 lunar day, which is challenging. Of course, we have this compressed operational schedule. We will have very little time, if any, to sit down and start analyzing the data from one operation to the next. So we have to pre-plan and pre-organize everything. We need to be prepared for as many scenarios and situations as we can possibly dream up. And we need to front load all of our key science. So we basically go for gold straight away. We don't just do some tentative measurements and try and find something, then decide whether that was a good place and we go back or whatever. We just go for gold. So we try to go to the optimum place, take the optimum sample, do the optimum science as soon as we possibly can, just in case things happen that mean we can't do subsequent analyses. We will interleave all of our sample acquisitions and analyses with other supporting science, such as imaging and permittivity sensors and temperature sensing, so get some context for the science that we're doing. And we will try to perform a very complete analysis as early as possible. I don't know why there's a full stop in the middle of that sentence, sorry. It shouldn't be there. That's what happens when you prepare your slides on a very long flight. The operations might also be tailored to shorten analysis and execution and recovery times. So we try and squeeze in as much as we can, try and do things as efficiently as we can, rather than just taking time, as I've said before. And we will try to develop and use fewer and far more complete low-risk operational sequences. So the fewer commands that we send up to the spacecraft, to the lander, the better. We don't want to do things with 100 different commands and then for things to trip over somewhere. We want one command which will then activate a sequence straight away. So that's the way that we're thinking at the moment. We've started work on this already. At the end of last year, we had an operational workshop at ESTEC in the Netherlands, where we started to discuss how we should proceed with this. We developed two nominal scenarios, what we were basically calling at a very high level wet and dry scenarios. So what do we do if we go somewhere where we find volatiles and ices in the soils? And what do we do if we don't? So those are the two basic themes that we have to work against. We have some scientific themes which were developed as part of our science objectives preparations, let's say, and we've tried to prioritize those themes against each of those scenarios. So of course the priorities might be different. If you land somewhere dry, you don't need to start looking for volatiles if it's clear that it's dry. Whereas of course the volatiles become the primary objective if you land somewhere where we expect to see the ices. So we've started prioritizing those themes. They will then get fed into the priorities for the lower level objectives as we work through that. And then that will in turn feed into the actual procedures and the operational sequences that we will develop. Some of these objective priorities will of course also need to be balanced with risk because some of these operations could be more complicated to achieve on the spacecraft than others. So we need to try and balance that into our prioritization and our sequencing as well. And it's clear as well that some of the operations might be able to achieve more than one objective. So all of these things need to be balanced and thought about. At the very high level for the operations flow, we already said that we should try and do what we're calling a full analysis chain as early as possible. So this will help to determine what sort of scenario that we're in. We'll immediately be able to see from our quick look data whether or not we see volatiles, whether or not we see ices. And that will help us determine exactly what we would want to do and which processes and sequences we would want to activate in subsequent measurements. So the full analysis would include a background exospheric measurement, some drilling and sampling at a selected location and to a selected depth, with regular multispectral imaging of what we're calling the cuttings pile, so the pile which builds up around the drill as we are drilling into the surface. We would then retrieve that sample, deliver it to Prosper, where we would image the sample before it is sealed in the oven, and then we would probably run an evolved gas analysis, so ramping up the temperature so we can immediately see if we have any volatiles in that sample and get some bulk chemistry from the sample. Then, for subsequent samples from the same location, this information will allow us basically to then run spectrometry through the magnetic sector, so stepped analysis, and that will help us give the context and understanding of the results that we're getting from that. From the very first analysis, though, after we've run the EGA, this evolved gas analysis, we would ramp up the temperature in the oven and do an ISIU demonstration, trying to extract oxygen from the sample as well. So this will basically give us a couple of very high-level key objectives very quickly. Subsequent samples would then need to decide when and whether we look for organics. Again, that depends on the scenario that we're in as to when we would want to do that. We'll run either pyrolysis or combustion on the samples. So we do have an option, a possibility to look for organics. And in a wet scenario, of course, it's important for us to preserve the volatiles as much as possible. The hardware itself is developed with volatile preservation in mind. So we're making sure that throughout that whole sampling and analytical process, we are preserving any volatiles that we might find within the regolith as much as we possibly can. So there's lots to think about, basically. The operations are complicated. We are very early on in the process of defining them, but we will get there. So that's where we are at the moment. For the next steps, we will aim to agree on what we're calling the basic nominal operational scenario and document that by the end of this year. Then we need to start thinking about the what ifs, and there are a million what ifs that we need to start thinking about and combining. We need to think about what happens if we land somewhere where we don't expect to land, what happens if we land upside down, what happens if we don't land at all, what happens if we don't get to the moon, what happens if we don't have as much power as we expect, if we have the wrong orientation of the spacecraft when we're in full sunlight. What if, what if, what if? We need to define as many operational situations and operational scenarios as we can. So as when we get up there, as much as possible, we can just decide which operational sequences to operate, push a button and get the maximum science back from the mission as we can. So outside of operations, a couple of other slides just for activities that we're following up on within the science team. As some of you unfortunately know in the room, we are right in the middle of a critical design review for Prospect. So some of you have a lot of horrible workload to deal with. From the science side, the important things there are for us to track the cleanliness and contamination and the volatile preservation throughout the whole chain. So we've been working on that, making sure that the documentation and the approach that we're following will provide us with as clean an environment as possible, minimize the contamination and maximize the volatile preservation. Part of that is managed through a contamination framework that's been put together and delivered by Open University. And that's been reviewed as part of the CDR by the science team. Generally speaking, we're looking good. So the science performance looks reasonable, and it looks like that with the current contamination control plan, we should be okay. The same is true for volatile preservation. We're assessing this as much as we can within the CDR, the critical design review. Previous work has demonstrated that the point where we experience the most volatile loss is the actual sample acquisition. So after we've drilled down to our depth, we push a tube out to retrieve the sample. And it's at that point where we experience the most volatile loss. So we're investigating that in more detail, looking at frictional heating, looking at other operational aspects where we can basically try to improve the volatile preservation at that stage. So stopping, letting the system cool down, for example, that sort of thing, waiting before we retrieve the drill. All of those things are being considered at the moment. One final thing that we've been working on, and you'll hear more about this in a presentation on Tuesday afternoon from Sarah Bozeman, is the landing site. So we've been looking at things from a prospect perspective, working very hard to try to find sites which we think are suitable. We will be on a static lander, and we are looking for volatiles, which means we need to select the site very, very carefully. We need to try and land somewhere where we have temperatures which are low enough for us to expect volatiles within the near subsurface, but which is illuminated enough to provide power, which is kind of working against each other. So we're doing the best we can to find these sites in the South Pole. We've put a lot of effort in to support NASA's landing site selection process for CP22, specifically with the Prospect hat on. So we've been looking at thermal aspects, especially for Prospect, but also looking at slopes and many, many other things. As I said, I don't want to talk too much about it because you'll have a separate presentation on that tomorrow afternoon. And I think that's everything I wanted to say. This is a summary. It's exciting times. We've got a lot to look forward to on Prospect. And if we're successful with our operations planning, I think we will be able to get some excellent science back when we finally fly. And I will finish there. Thank you very much.
Questions? James?
Hi, Melissa Martineau from the University of Lorraine in France. This might be a really stupid question, but you mentioned that the critical point of volatile loss would be the drilling part. What about the blast from the landing? Would that only be on the really surface, or like how deep do you plan on drilling to escape that?
Yeah, that's an important question. There is no such thing as a stupid question, and that's a very important one. It's something that we do need to analyze. It's more important from the contamination perspective than from the volatile preservation perspective. We need to think about the impact of the lander plume itself, how much of that is digging out, and how much contamination that is going to provide. But from the thermal perspective, we don't expect it's going to have a big impact on volatile loss, because the moon is a very insulating, the regolith is very insulating. So basically, after we've blown all of that stuff away, if we drill down a few centimeters, we will still experience temperatures where water ice should be stable. So it's more important from a contamination perspective rather than a volatile perspective.
Hi, Eileen Yingst, Planetary Science Institute. I'm assuming that Prospect is flying with some other payloads. Do you have an idea yet, since you're working on the operations, how much time is going to be required for your instrument to, you're right, this is complex and there's a lot of stuff going on. Do you have an idea of how much time during a single Earth day that you would require?
Yes, how it's going to be weaved into the overall operational process with all of the other instruments and payloads is still TBD. A full operational cycle for us could take up to 16 hours. Yeah, so, but there are several points within that process where we can pause and we can wait for other payloads to do things. There are several points in terms of managing the temperature and the volatile loss where it's preferable for us to wait. So a total process is about 16 hours, up to about 16 hours.
And how much perhaps for, because I'm assuming that that you would be looking to see if there's volatile loss during that period for like the first bit. How much time do you think, give or take?
I'm not sure I understand the question, sorry.
So 16 hours soup to nuts for the really crucial stuff at the beginning of the process, at the beginning of the drilling process. How much time do you think?
The drilling depends on how deep we go, but that's not going to be, again, because the moon is so insulating, we expect the temperatures to be fairly low after you've gone through, if we land at the right place, after we've gone through the first centimeter or two. It's not going to matter from a volatile loss perspective. So the time it takes for us to drill and sample will depend on how deep we go, basically. That's it.
Thanks.
Yeah.